Hello ladies and gentlemen, my name is Dylan Hamilton from C.A.R. Entertainment and welcome back to another AS1 biology revision video. We're moving on from cell physiology on to osmosis, and then we only have two more left with cells and we'll be done with it. I do hate cells. I'm pretty sure you're tired of me talking about cells, but we're going to get through this together, guys, and I can assure you that by the time we finish cells, you should be prepared to go into your exam and absolutely nail every cells question out off the park, even on the CS spec in Northern Ireland. Let's get straight into this video about osmosis. So now, the osmosis definition changes from GCSE as you change the words from high concentration to low concentration to you change concentration to water potential. As the definition of osmosis now is the net movement of water molecules through a partially permeable membrane from a high water potential to a low water potential, and that is exactly, leave a single word out of that and you'll probably be put down a mark. You need the net movement of water, you need partially permeable membrane, you need high water potential and low water potential. Let's talk about what the hell is this word water potential. Water potential is essentially just the tendency to take in water by osmosis from pure water across a selectively permeable membrane measured in kilopascals. Pure water will have a water potential of 0. Water molecules are free, and so they do not form associations with other molecules, and some water molecules will not be free, so they will form hydration shells around these solutes. The presence of solutes will reduce the ability of water molecules to diffuse throughout the solution. There's 3 different types of solution. You will have a stronger solution, which will be classified as hypotonic. So you'll say, oh, you'll add a hypotonic solution, or you'll whatever. You have a weaker solution, which is hypotonic, and then an equal concentration, so it's equal solutes, equal water, all out there jazz. That's going to be isotonic. So essentially, the meaning of water potential. It is the measure of free energy available for water molecules to move, and the presence of solutes will hinder the ability of water molecules to move, as we previously mentioned. Now, free energy will be available in pure water greater than the water molecules in solutes. 0 is the highest water potential you can get. It will not go positive other than 0. It's all negative. Presence of substances dissolved in the water will lower the water potential, and the water potential of the solution will be always less than 0, as we just said, so it's always negative. The solution will have a negative water potential and have some water in the hydration cells, and this means it's more concentrated solution with a more negative water potential, meaning it's increased likely to take in water by osmosis. Now, there's a couple of different components you'll need to know. Basically, when combined, the opposite actions of solute potential and pressure potential, so they have opposite actions. The solute potential is the presence of solute particles and the potential of cell solution drawn in water by osmosis. Okay, so pure water has a solute potential of 0, as in there's no solute. So pure water is 0 water potential, 0 solute potential. Solutions usually have a negative solute potential though. With a more concentrated solution, the more negative your solute potential will be. So solutes will decrease your osmotic potential, and the pressure potential will only apply to plant cells as they have a cell wall, and turgor will be involved. Now, water potential is equal to the solute potential plus your pressure potential. That's why we say that they're combined to give your water potential. So your solute potential of a cytoplasm is the main factor determining the water potential of the animal cell. And the animal cell is water potential equaling your solute potential, because there's no pressure potential involved. So osmosis in plant cells, part 1. It's quite a long story, but it's a story nonetheless, so it sort of helps you get across it. So basically, the protoplast of the cell has a cell sap, and the cell will have a lower water potential than pure water. So as water enters through osmosis, the protoplast will expand until it presses against the cell wall with turgor pressure. Now the cell wall will oppose this with an equal magnitude wall pressure. Expanding cell will have a tendency to push water out of the cell, and the water in the cell has a pressure potential which is always going to be positive. Pressure potential can be positive. Now if you place the cell in a hypotonic, which is less concentrated than the protoplast, this higher water potential will mean osmosis will occur into the cell, meaning the protoplast will swell, pressing against the cell wall. Now in the isotonic solution, which is the same concentration and the same water potential, osmosis doesn't really occur, and the cell membrane will just about start to pull away from the cell wall. Now if you put it in hypertonic solution, which is more concentrated in the protoplast, this will lower your water potential all the way down, and osmosis will go out of the cell, meaning the cell will become plasmolyzed. So let's go on to the story then. As your cell takes up water, your pressure potential will rise and your protoplast will press against the cell wall, and the expanding cell will rise towards 0 as the cell becomes fully turgid. Your solute potential of the expanding cell will be less negative, and the cell sap will be diluted by the uptake of water. Your cell will lose water, so the membrane will begin to pull away from the cell wall and the pressure potential will become zero. Incipient plasmolysis will occur, and when the cell loses water, it will then become fully plasmolysed. So moving on to part 2 and expanding on from our wee story. Basically, plant cells rely on this turgor for support, and the opposing forces of the cell membrane and cell wall will create turgor for support. Plant tissue having a shortage of water will mean the cells will cease to become turgid, and so they will become flaccid, and a large number of flaccid cells means wilting will occur. Now, plant cells may lose too much water and the vacuole will shrink, and the extent to which the cell membrane will pull away from the cell wall called plasmolysis, and the cell will be plasmolysed. So basically, when you lose too much water, the vacuole shrinks, cell membrane pulls away from the cell wall, plasmolysis will occur. But this does seldomly occur, as cells are unlikely to survive if they're plasmolysed. Now, a situation in which plasmolysis may occur is whenever a plant is grown in a field which is given too much fertilizer, or you have seeds from a woodland tree which is carried to the salt marsh when it's starting to germinate in the environment. The point at which the cell membrane begins to lose contact with the cell wall is incipient plasmolysis. Now we're going to do osmosis in animal cells. Now animal cells do not have a cell wall, so there's nothing going to stop the expansion of the cell membrane until it basically just bursts, or a better word to use would be lysis. Now when lysis takes place, the animal cell is usually placed in a hypotonic solution, and the animal cells in the hypertonic solution means the cell will lose water and they will shrink to become shriveled up, and this is called crenation. Thank you, ladies and gentlemen, for watching our osmosis revision video. I've been Dylan from C.A.R. Entertainment, and I'll see you next time.